So we are recording live, and you guys can all see, right? Okay. So we're going to talk about motion, and we're going to go a little bit further with derivatives. So first, let's kind of talk about some of the notation that you're going to see moving forward. Okay. So we've already talked about this. Okay. F prime of x. Usually, if we have a function of y, we could also write it as dy dx. Okay, and you need to be really comfortable with how you are saying these things, right? This is called f prime, and you read this as d, like dy dx. Okay, and then if we take the derivative of the derivative, that's called f double prime of x. The notation looks something like this. So you have d squared y over dx squared. Getting ahead of myself there. Okay? And so here this is read as f double prime. And here you read this as d squared y over dx squared. Okay? And this, if you were to keep going, you could take triple derivatives. You just follow the pattern that you're doing here. So instead of d squared y over dx squared, it would be d cubed y over dx cubed, and so on. So eventually, if you go up to the nth derivative, okay, usually once we get to a high number of derivatives, instead of doing the prime notation, like if we had the sixth derivative, you're not going to see 1, 2, 3, 4, 5, 6 marks. I mean, you could do it that way, but you're not going to see it that way. What they'll do is put the number in parentheses, and this means the nth derivative of f. And then you would still write it the same way as we've been doing with the d dx notation. It'd be d to the n y over dx to the n. Okay, so that's how you would write higher order derivatives. Are there questions on the notation? Okay, we're not going to see much higher than first order derivative and second order derivative for now, but it's worth mentioning what they look like so that when we get there, we've already seen it ahead of time. All right, first example. Let's say we have f of x equal to 3x squared plus sine of x. And I want you to find f double prime of pi over 2. All right, so to get to the second derivative, you got to find the first derivative. So let's do that. So f prime, let's see, who can tell me what f prime is going to look like? Go ahead. Brandon.
Okay, so it'd be 6x plus cosine of x.
Good. And now someone besides Brandon, what would f double prime of x be? So all we're doing now is just taking the derivative of the new function.
Six minus sin.
6 minus
Sine.
sine. 6 minus sin. 6 minus sine of x. Yeah, don't forget the x. We need the x in there, but that is correct. Perfect. we're pretty much done, right? So now how do I find f prime of double 2, or f double prime of pi over 2? You just plug it in. So it'd be 6 minus the sine of pi over 2, the sine of pi over 2. Hopefully we're starting to remember our unit circle at this point since we keep doing trig every now and then. What's the sine of pi over 2?
1.
And so here we get an answer of 5. Okay? Any questions on that? All right, let's try one more, and then we'll step it up a little bit. Let's say we have v equal to t to the 4 plus 6t minus 8. And I want you to find d squared v over dt squared. And so this is going to be new notation, so I'm going to go ahead and introduce it. When you see a line after this with a little subscript like that, t equals 4, it pretty much means the same thing we did up here. What you want to do is find the second derivative, and then you evaluate it or you plug in t equals 4. That's what this notation means. Okay, so you'll see that pretty frequently. So don't get confused and thrown off by it. We know how to do it. So let's go ahead and find the first derivative. Let's see. Who can I call on here? Mason, what would the first derivative be?
I'm not too sure.
All right, let's help him out. Isha. Isha has left the meeting. Okay. Let's try Adam. You guys do realize if I call on you and there's no response, I have to mark you absent, right? Oh boy. Okay. Adam. Isha. Oh man. AP Calc AB Premiere on YouTube isn't going so well today. All right. Shamira, can you tell us the derivative?
I'm still trying to figure it out.
Okay.
Mr. Gonzalez, I can help you with that.
All right, Ethan, take it away.
The v prime would be 4t cubed plus 6.
Very good. It's just the power rule, right? If you guys haven't been doing your practice, okay, you're missing out because eventually we want to get to a point where we see this type of function and we know the derivative in like 2 seconds, okay? So we got to practice and make sure that we're remembering our power rules and our trig rules. Okay, let's go one more step since I need to find the second derivative. Mike, what would I do to find the second derivative?
Give me a second.
Okay.
Twelve t squared.
Uh-huh. Very good. And now finally, to do this, you're just going to plug in 12, or not plug in 12, sorry, you're going to do 12 times 4 squared. And so help me out, what's 12 times 16 going to be?
$192.
Perfect. Okay. Any questions on that? Okay. Now let's step it up to physics applications. Okay, so how does this all relate to something like this? So let's say I give you a graph, a position versus time graph. Let's say time is in seconds, and the position is going to be in feet. And we'll just keep it real simple. We'll go up to 5 on the x-axis. Then we'll go up to 4 on the y-axis. And let's say I go from 0, 0 to 1, 2. And then connect over here to 2, 2. And then we're going to go up to 3, 3. Connect over to 4, 3. And then we're going to go straight down over to 5. And so here are some questions that you could be asked. Okay, A, what is the slope at t equals, let's say, 0.5 seconds? And what is happening? B, same thing, at t equals 3.5 seconds, and we'll do the same with t equals, let's say, 4.2. All right. Oh, Isha's back. Okay. Isha, can you tell me the slope right here at t equals 0.5? So right there at that point, what would the slope be?
I don't know.
How do you find the slope just by looking at a graph? What's the basic?
It's over on.
Right. So you see that this point is part of this segment, right? So even though we're looking right here, it's going to be the slope that is everywhere from this point to that point. Does that make sense? And so
Yeah.
from here to there, what's the slope going to be?
2.
There we go. So the slope is going to be 2, and let's put units here because units are going to be very important, and it'll help us interpret what's going on. So we're increasing 2 feet, right, per 1 second. And so if this is a position graph, whether it's an object, a particle, a person, doesn't matter, okay? Whatever is moving, here's where it starts, okay? So this is the starting position. And it's moving away at a rate of 2 feet per second. Does that make sense to everybody? Because that's the slope for that first section, okay? So what's going on? We are moving away from starting location at this rate. All right, let's try B. At 3.5, what's the slope at 3.5? So it's going to be whatever the slope is for that segment. Maybe Mason can help us out with this one. Say it again.
0.
0 is correct. Very good. So slope there is 0 feet per second. And so what's happening then at this time? Are we moving? Correct. We're not moving. Yeah, we're standing still. Okay. And Johanna, what about at 4.2? So somewhere on that section, what would the slope be?
0.
At 4.2, which ends up, well, this point should be exactly at 4, so it might look like, so let's go like right about here. What would the slope be for this?
Negative 5x.
Careful with that. Let's do rise
No,
over
yeah.
run. Say that again, sorry.
Would it be negative 5?
It would be negative, but it's not 5. How far are we going down?
Negative
1, 2, 3 over 1, right? So that's negative 3. Oh, switch colors again. Negative 3 feet per second. Okay. And we are moving. So remember, if this is position, right here at this segment, we are 2 feet away from where I started. Here, during this time, we are 3 feet away from where I started. But now, as soon as we hit this blue segment at the end, now we're moving back towards where I started. Does that make sense? So, moving towards starting location. So that's kind of how to look at a graph and understand and interpret slopes and how this all relates. By the way, in calculus, what have we been calling slopes? Begins with a D.
Derivative.
Derivatives, yes. Okay. So if I were to ask you for the derivative of this graph at the same exact locations, your answers are going to be exactly the same, right? So let's actually write that down. So some common notation. S of t usually is going to stand for position. If I take the derivative, okay, so all these slope questions that I asked you represent the velocity of whatever's moving. So we just call that v of t. And to find it, you just take the derivative of the position graph. Because if I want to find the slope, you just take the derivative, okay? And so, and hopefully that makes sense, right? The rate of change, feet per second, that's the rate of change. That's going to be the velocity. If I were to take the derivative again, that would give us the acceleration. And there's a couple of ways that you can write the acceleration. If you take the derivative of the derivative, Okay, it'd just be the second derivative of the position graph, or you could write it as the first derivative of the velocity graph. Okay, and the units are something like feet, feet per second, and feet per second squared. Okay, the velocity is just a rate of change attached to feet and seconds. Acceleration is going to be a rate of change when you're comparing velocities. So if you take feet per second, that's how we get feet per second squared. Okay, you do need to be comfortable with those units. And so we're going to do a couple of quick examples to end class with. I may go a couple minutes over since we were a little slow to get going here. But if you need to leave, I get it. If not, I'm hoping that this video records properly, and I'll just post it if you need to take off at 3:25. Example, what is this? 3. If t is in seconds and s of t equals negative 16t squared plus 6t plus 48 is in feet, find the velocity and acceleration at t equals 3 seconds. So you have a position equation, and we're just looking for the velocity and the acceleration at this specific time value. Okay? So whenever you see a question like this, it's actually going to look exactly like the problem that we did for example 1. It's just now we have physical meaning attached to it. Does that make sense? For example, when I find the first derivative, that's going to be the formula that gives us the velocity. When I find the second derivative, that's going to be the formula that gives you the acceleration. So we're going to do exactly what we did for example 1. Okay, the velocity is just going to be the first derivative. Okay, and so I'm going to go through this myself because we're running out of time. You do the power rule. So 2 times negative 16 is negative 32. Decrease the exponent, so now it's just t. Same thing here. And then 48 drops out because that's the constant. Okay. Acceleration is just going to be the derivative of the velocity. So again, power rule. We're just using the power rule left and right today. This is just going to be negative 32. Okay? So at t equals 3 seconds, the velocity, you just plug 3 in, so it'd be negative 32 times 3 plus 6. And so what is that? Negative 96 plus 6 is negative 90. So it'd be negative 90. And please make sure you're always including units when there's units involved. Okay, an AP exam is going to be loaded with units everywhere, and you got to make sure you convince the graders that you understand how this is all related. This is a velocity, so this is feet per second. Acceleration, well, according to what I just calculated up here, the acceleration is always negative 32. Okay, so it's negative 32 feet per second squared. Okay, one more little concept. Again, I apologize if you need to take off. Like I said, you can pick up the notes. And I'll post a link on Schoology to the video. But the last thing we needed to talk about is average velocity. Over an interval from A to B. And all you need to know, it's still change in position over change in time, or change in y over change in x, right? So we're still finding a slope. And so actually for average velocity, there's really no calculus involved. It's literally just finding the slope between 2 points. Okay? So for example, if you have a graph and we look something like this, let's say this is f of x, and you want to find the average velocity, you're literally just going to connect and you find the slope between the 2 points. And so if you write out the formula, you're going to do y2 minus y1. In other words, plug in b, plug in a, so you figure out what the y coordinates are, over x2 minus x1. So your x2 here would be b and your x1 would be a. Okay, it's just the slope. But this is the formula that you guys should remember for average velocity. Okay, and so here's a quick example to end class with. If you have a position graph that is represented by t cubed minus t squared, what is the average velocity over the interval from 0 to 5? Okay, so again, if you just remember, oh, I'm just finding the slope, right? You're going to take, remember this is like your A and B or your x1 and your x2 down here, right? You plug both of those in, so you're going to do s of 5 minus s of 0. That's your y2, that's your y1, minus x2 over x1, which is 5 minus 0, and you just figure that out. You plug in 5, you're going to get 5 cubed, plug in 0. Oh, sorry. Getting ahead of myself there. Let's rewrite that. You're going to do 5 cubed minus 5 squared minus, and now if you plug 0 in, when you plug 0 in, that's obviously going to be 0. And then 5 minus 0 is 5. And so really the only thing left to do is figure this out, which is 125 minus 25 over 5. So just arithmetic at that point. 100 divided by 5 is 20.